Hello everyone, welcome to this session. In the last session, we have introduced the workflow and key operators of PSO. So in this session, we will use an example to demonstrate this workflow. So first of all, let's review the PSO flow diagram. First, we consider a solution in the search space is the position of a particle, right? Then we do the following steps. We have a population of solutions. We track the two extreme values. So what are the two extreme values? The p-best and g-best. So p-best is for each particle, g-best is for each iteration. Based on the p-best and g-best value, we can update the speed and position of each particle. Then we get new solutions. And then we use the new solutions to replace the old solutions. We get another population. Then we go to this process again and again until the stopping criterion is met. The key is here, update the speed and position of each particle. So last session we discussed this formula, right? So the VIT plus 1, the particle i's velocity in the t plus 1 iteration is equals to this, the inertial rate multiplied by the velocity of the particle I in the tth iteration. And consider here the C1 and C2 are what? Are the learning rate, right? And the R1 and R2 are random variables. So here we have the p-best I, in the tth iteration, the p-best value of the particle I. This one is the g-best value of the tth iteration. Then we minus the current xit, right? The position of the particle I in the tth iteration. When we get the VIT plus 1, we will get the xit plus 1 by this formula, and xit plus the VIT plus 1 from here. So this is what we introduced in the last session. Now we will see an example and how PSO algorithm solve this problem. So the problem is that we want to minimize the x to the power of 2 of second and plus 1, right? So the x is between minus 10 and positive 10. So clearly from this one, we can see where is the optimal value of x. X equals to 0, right? And the y equals to 1. So this is the 1. So let's see how PSO algorithm can find this optimal. Okay. First of all, we need to initialize the population. Let's see the iteration is equals to 1, t equals to 1. The first particle, p11, this one means the first particle. This means the first iteration. So we randomly put them in, so we can say x11 equals to 8 and the v11 equals to 3, right? So this is the randomly initialization of the first particle. Then we can do what? We can calculate the p-best and g-best, but we can't calculate the g-best now, because the other particles are not available yet. So we consider this population have 3 particles, right? 3 particles, but the other 2 is not there yet. But we can get the p-best. So p-best of the particle 1 is what? First we can calculate the f11, the particle 1 in the first iteration, 65, right? So because this is the first iteration, so itself is a p-best. So the current best value is itself, only 1 iteration. So that is 8. Similarly, we can do the same thing for the particle 2 and particle 3. So we can see for particle 2, the position is minus 5 and the h value is 26. Then we can get all of that, right? The p-best 1 and this. So when we get the p32, the particle 3 in the first iteration, we randomly initialize it to minus 7 and we get an objective function of 50. Then we have the p-best 3 is this minus 7. So in the first iteration, we get 3 p-best now. The 3 particles, each one have a p-best. Now we need to do the g-best. The g-best is for what? Is for this iteration. So we can see here we get all the 3 positions and velocities. That based on positions, we can calculate the function value, the f11, f21, f31. Then we can compare this to find the best of them. So it's a minimization problem. So this one is the best, right? So we can see the f21, this is has the best objective function in the initial population. So G best equals to P best 2 1. P best 2 1. So the G best is -5. Right. So now we finish the first iteration. So then what we should do? So we should now we get the P best and G best, right? So what we should do is to update the speed and position of each particle. So how to do? Through the formulas we have just introduced, right? We have just shown you. So we can see the update the particle speed and position. Here we say C1 equals to C2 equals to 2, and the omega is 0.5. It's a common setting, right? So now based on the particles speed and position, we will calculate the next iteration's speed and position. So here to make it simple, the two random numbers, I make one of them to 0. But in reality, they are all the values between 0 and 1. So we can see how to calculate it. We want to calculate the V12. So this one becomes using this formula, and P best 1 G best 1, we already have them, right? So V11, we already have them. So based on the previous value, we can calculate V12, the velocity of particle 1 in the second iteration, right? Then based on the other formula, we can calculate the position of the particle 1 in the second iteration by this formula. So we can find the velocity is 1.5, the position is 9.5. So these numbers are not important. The important are the procedure, right? So then what we can do collect the value of the P12, right? The particle 1 in the second iteration. So similarly, we can do the second particle, P22, right? So this time I also put one of them to 0. Similarly, we can go to P32. So this one, I don't repeat the process. The process is the same. So till now, what do we have? We have the population of the second iteration. So these values are calculated here as we have previously done, right? So now for each of the particle 1, 2, 3 in the second iteration, we have their velocity and position, right? So what we should do next? After this step, we have the new solutions. The first iteration solution changed to the second iteration's one, right? Now we need to replace this to a new population of solutions. So this one becomes the solutions of the second iteration. We should again go to this, track two extreme values to get P best and G best, right? So this is the second population of the population of the second iteration. We can calculate the objective function value for, let's say, the first one. Particle 1 in the second iteration, the objective function value is 91.25. So in the first iteration, the F1 is 65. Because this is a minimization problem, so this new value in the second iteration is worse than the one in the first iteration. So we can say what? That the P best 1, 2 remains the previous one, because the previous one is better. So the current in the second iteration, the best value is the previous one, for particle 1, right? Because the new value is worse than that. Similarly, for particle 2, we can still do the same thing, and we found, okay, this value is still larger than the previous one. So for the particle 2 in the second iteration, the current best is still the first iteration's one, so -5, not this -6.5. For particle 3, we find that, okay, when we use this value, we found, okay, this value is smaller than the previous one in the first iteration. Therefore, for the third particle in the second iteration, the current best value is x32. So it's for this value. This is -4.3, so it's here. And for the third particle, we use the position of the particle 3 in the second iteration, right? So in this way, what we can do is that now we have the 3 P best. Then we will see which one is the best one in the second iteration, the third one, right? Because this 19.49 is better than this and better than this. So the G best in the second iteration is a third particle, P best 3, 2. So the position is minus 4.3. So in this way that we again get the P best and G best. So we will do this again. For the third iteration, we update the speed and position of each particle. So we do the same thing, calculate the P13 and V13. So the calculation is here, and I do repeat, you can see it yourself. Similarly, we can do the particle 2 for the third iteration, particle 3 for the third iteration. So now we get the population of the third iteration. So we can again update the P best and G best following the same process. So you can see it yourself, right? So as we can see, after the 3 iterations, we find the best fitness is here, minus 0.79, and this is the x value of the first particle in the third iteration, and we can find this is not far from 0, the global minimum, right? So we can see the G best 3 is this. Then we will go to the next iteration. So here is a table that we summarize in the 3 iterations. So what are the 3 particles, the current solutions, the particle's position, and what is P best now for each particle, and what the G best for each iteration, and what is the corresponding objective function value. We can see this is the best that we can find in 3 iterations. So if the termination conditions do not meet, we will continue the iterations, right? So otherwise, we will output the G best and the program, right? So thank you very much. Bye-bye.